So we're handing over now to Peter Grove, who's a distinguished member of the technical staff at Renesas, and Graham Nunn, who is at Cirrus Logic. He's a manager of mixed signal modeling and verification. So our two main companies today, which helped to put this event on, are Renesas and Cirrus. So thank you very much to Renesas and Cirrus. And they're going to talk about what is mixed signal verification and why you might want a career in it. Okay, and there's two parts to this. I think we have the break in the middle.
Yeah,
Don't we?
we've got so people can leave if they.
Yeah, no, you got. It's two lots of 30 minutes with a break in the middle. Okay. Peter has 20 years experience of mixed signal design as well as EDA tool and methodology development. Peter has led many high volume production devices in the past. Is a chair of SVAMS, which I'm sure I'll explain to you, and a key contributor to UVM AMS. Again, I assume
that will be, yeah.
That's going to be in there. And the 1800 adapters discussion, sorry. Peter's presented at many conferences and he's a regular presenter at Synopsys as well.
Yes.
As was. And recognised for his skill in mixed signal verification. He's based in Edinburgh. Graham joined Cirrus Logic in 2016. He has over 25 years industrial experience in development and verification of high-performance mixed signal integrated circuits. He has a background in analog and digital design and has a passion for developing innovative solutions for mixed signal chip development, again based in Edinburgh. So I'll hand over to him.
Yeah. So
do your bio first.
So look, this set of slides is really geared towards students. So there's done maybe some assumptions in the slides. There's probably going to be typos as well because we work for different companies. There was no spec, and we met up a few times where we were allowed to. I'll go through a bit of my background first, then Graham will go through his. I left Edinburgh University with an MEng in about 2000. I went and worked at a company called Wolfson Microelectronics, where I met Graham. The company wasn't on the stock market then. The building wasn't great. When it rained inside as well as outside. There's many other stories like rats running around while you're trying to design microchips. But we were exposed to a lot of mixed signal concepts. And the company was not well off, so we had to come up with novel ideas of how to verify a design and get that confidence level that Mike's on about to tape out and get them into customers. So we sort of a startup winging it quite often, which is a bit like we're doing with this presentation today. From there, Wolfson floated on the stock market. I got heavily involved in running chips. I did 18 plus chips in 12 years, which nearly burnt me out. And then I decided to go and work at different companies. So I moved on to Renesas, where I've sort of ended up in a role of doing a lot of mixed signal methodology flows. I've got dragged into doing some of the standards, and I work a lot with the EDA vendors. So they'll probably pick on me at their presentations later on. If not, they'll pick on me now. It's revenge. But I'll let Graham introduce himself.
And laptop's gone to sleep, so no mind.
Should have planned that.
Yeah. So if specification doesn't work, normal things. So I'm Graham. As I said, I met Pete back in sort of 2000 when he joined Wolfson, but I'd graduated a couple of years before. You did MEng as well?
Yes.
So both of us did the MEng, and as Pete says, it was a fascinating place to work. And if you look back at what we were doing that time, it was really actually quite innovative, but it wasn't industry standard in any way at that point. So it's a really interesting time. So as I said, I've sort of been doing analog design primarily up until about 2016. But when I was working for a startup in 2011, my boss challenged me, well, we've got this new standard called UVM. can you run AMS sims through it? Can you run not just the digital stuff that Mike's been talking about, but can you run the analog through it as well? And just went, no idea. Let's have fun trying to find out. So that spiraled into me becoming primarily mixed signal verification engineer when I joined Cirrus in 2016. And yeah, the rest is history. It's been a really interesting journey seeing what the tools will let you do. And I'm just fascinated by what tools are available, what methodologies are there. And I think the biggest change was realizing how poor things were and realizing that using your technologies, you can do far more. So yeah, that's what dragged me here.
So Graham uses the tools. I break them and push them to the nth degree, where the vendors get quite annoyed with me.
Yeah, have something to aim for.
Right, so we've got our picture on the top corner because, as I said, we're winging it the first time, so we can't remember the slide deck off the top of our head. We've actually got proper jobs to do as well as this. So Edinburgh, you might think is just, you know, a small city in Scotland, probably has nothing to do with much in the way of silicon manufacturing, but there's actually quite a lot of companies here. So I pulled up a map with the help of Graham telling me how I do this on Google, because I didn't know. And you can start to see, let's see if I've got the pointer. Yeah, so you can start to see there's actually quite a lot of companies dotted around. And this is just Edinburgh. There are, you know, Glasgow and probably Livingston, other places. So when you're looking for placements, this slide will be shared and it's got a list of companies on. You could start with them, but there are probably others. So we put them in alphabetical order. Not to say one's better than the other. A lot of them will do some sort of mixed signal. I can't tell you all of them of what they do, but they'll all do some sort of level of verification. You know, and it's a small community, so a lot of us do know each other. We've worked together before. You know, that's how Graham and I been allowed to do these slides together. There's an element of trust between our companies that we're not going to give information away. So I'm going to go through some slides. We're both going to go through some slides. I'm going to go through some basics of analog and digital design because there's second-year students online, so I can't go in and put some complex mixed signal design because I'll have lost them on slide 3 and they won't come back after the coffee break. Then I'm going to go through, if I could even see the slides. I'm going to go through, you know, part of what Mike went on about the specification, the verification, and the design space, and probably how it works in real life. Then I'm going to go through a very simple example of a digital to analog converter. Graham will go through the design block, and then we should have a bit of time before the first coffee break to have a few questions. That's the plan. So let's get back to basics. We've got a digital circuit can be thought of as a light switch. It's either on or off. There is nothing in between. We use Boolean logic, and it's all event-based simulation. So like where Mike said, varying the clock when he runs his simulation, does that make a difference? It doesn't. It's just a simulation, and it's either on or off. You give that problem to an analog engineer, and they turn it into a dimmer switch. They won't tell you whether the light's on or off, but it might be, might not be. Is the light switch complete? Might be, maybe next week. That's the sort of response you get from an analog guy. You've got infinite number of states as well. 1 volt or 1 volt plus 1 microvolt. Are they different? I don't know. It depends on the application. You know, in some places that will make a big difference. In others, wouldn't. I mean, as a guess, I imagine a codec or 1 microvolt difference would make a difference. It's based on differential equations, so it's not on or off. It's, you know, you've got here your capacitor equation. That's meant to be your MOS equation. That's what you talk at university. The equations that you then put in a simulator are not like that. They're massive. And they don't write equations like that. They're curve fitted. So an analog simulation circuits are quite involved. and the simulations are basically continuous in time. So they're not clock driven, and they use matrices to basically solve the circuits, where a digital one is more like a bit of software that you're running. So someone made a song years ago called "We Live in a Material World." I think they would have actually sold a lot more songs if they'd changed it and said "We live in a material world," if that stupid sign would be out the way. Hadn't coped with that. So yeah, we do. We live in a mixed signal world. You know, we don't have a digital head. We don't have a digital brain that we can plug into our phone. We have to speak. The phone has to translate that into digital code that gets transmitted digitally around the world, goes into a DAC, goes into someone else's speaker, and they can speak back. And it doesn't matter if the other side of the world, all the noise cancelling, all the delay is being taken care of. So it sounds like they're in the room. But we've got the fundamental problem. We are analog. We're not digital. You know, so everything we do is going to be mixed signal. You know, your CPUs on your laptops, yeah, they're pure digital, but you interact with a keyboard. Your keyboard is converting your analog fingertips and our words into digital codes. So let's see if I come on. Right. So years ago, when I grew up, that was the top-notch phone that you had to replicate your kids. In fact, I saw it on TV the other night. So it was probably analog based, might have had a bit of digital circuitry in it. It had very few options. It basically did maybe one thing. And I would argue back then you got 100% verification. There was no quibble as to have we covered it or not. It probably played one song. You know, nowadays you go and get a phone for a kid and it looks like that. And I'm talking about the toy ones now. It will have a CPU, microphones in it, speakers. You cannot even verify the kid's toy now, let alone your own phone, because there are so many combinations it can be used in. So that state space Mike was on about is massive. You know, lots of digital processing. You know, the kids can probably book their Oasis tickets and get them, which is and sell them again to your adults that want them. Yeah, anyone who's got Oasis tickets for sale, I'll meet you afterwards. And the music comes from, you know, in a digital form, you know, either from Spotify or one of these other ones. In the olden days, it would have come from, you know, a sort of mini disc or things like that. And then it's converted so you can hear it in your ears, which again are analog. So Cirrus are well known for doing high quality DACs and ADCs. So sort of why we chose this, because we can relate to it. Now, the historical design never had a product recall, didn't need software updates. Who's had a phone that they haven't had a software update on? Or bought a bit of software in the last 10 years that they haven't had an update on? In fact, I think most people's phones do an update of one of the apps overnight, every night. You know, and that just shows that it's damn near impossible to verify everything and get it right first time nowadays. Also, like the modern designs, you need more verification people because there is more state space. There's more things you can do with it. So you either wing it out in the market and go, here's a phone that should work, and wait for all the feedback that they don't like it and gradually fix the bugs. But you probably won't have customers, or you have to do a lot of work up front. So part of this presentation is to show that, you know, there's a lot of work in verification. It's actually, you know, it's probably the bigger part of any design process now than actually designing it. You don't tend to change the design. You'll constantly evolve the verification to get it better and better and cover more stuff in less time. Oh, Graham, it's you next.
Yeah, I'm up next. Fine. So try not to break things. I mean, this is sort of carrying on from where Ben and Vlad and also Mike have carried on, is that fundamentally we are building things for customers. The customer could be you as an end user, or predominantly from chip manufacturing point of view, it's more the integrator, whether it's the Apples or Samsungs of this world, that they are our primary customers. And the challenge is you've got to create a design which meets both users' needs. So if you think about it, if we design something which takes too much power, you end up with a VR headset where you've got a several kilogram battery pack next to you to actually make the thing worthwhile. It doesn't fulfill the need. So if you think about, if you provide something and the end user that implements it and it doesn't actually work. I don't know if you remember a few years ago, it used to be that the speakers on your phones would eventually start distorting and start decaying. Well, that was because the speaker drivers on the chips were overdriving the speakers. Speakers are getting too hot and breaking. So that makes the reputation of the phone manufacturer look poorer because they have things which break over time. So the goal from a chip point of view is to make sure that needs are met. The next one, as already been talked about, is delivering things on time. The consumer electronic space, Mike was talking about for several years for chip development, but for somewhere like Cirrus, you are developing over maybe 18 months or shorter. And you do have to hit the specific windows for manufacturing. So if you are late, you may lose 6 months, as Mike was saying, of revenue. You may lose several years worth if that design slot carries on. So it's the goal of what we're trying to do is get to the point where you've got the as Mike was putting it, the satisfactory quality level. And how do we get there? So if you're doing something as an iteration, it's probably a more simple step for you. But if you're doing something new, then you're doing high level verification of the concept. So using maybe MATLAB or mathematical tools or just hard maths to actually prove whether the thing is worthwhile doing. And then onto the detailed checking. That's primarily the grunt work that we're talking about here with verification of getting to the point where it is good enough that the customer will be happy, but also that you haven't wasted too much effort on it. It hasn't cost you too much to produce it. So from Pete's example with the phone, you understand that modern mixed signal designs are fiendishly complicated, but it's not just hardware. You also have software and driver level for the users, as well as firmware, as in code which is running on the individual chips, doing sort of DSP control, that sort of thing. And so from Pete's example and from the Siemens report, the number of verification engineers you have for each designer may be up to 5 to 1. So actually checking things is a more valuable task in a way than actually doing the implementation itself. So it's a huge task. Anything I need to say? So again, you're looking at the issue with you're throwing lots of effort with verification, but verification can easily become the gating factor in getting the design manufactured. So not only do you have to throw lots of effort at it, you need to be very efficient at it and also know when to stop. All these things are in there as things need to wrestle with. So the mixed signal design flows that Pete and I and others have been working on over the last sort of decade or so are really trying to push to get to first time success and on time delivery. That's the focus, and trying to work out how to optimize those things using the new techniques that are available to get to that point. So I think Mike's talk earlier on with the wrestling with having a perfect specification to start with. I don't think I've ever had a chip which is at a perfect specification to start with. It's sometimes the user knows what they would love, but that's unimplementable. Sometimes the people who are defining the specifications internally, they have a good idea, but maybe not all the way to the depth. So this is the idealized process, but then I'll say how it's not. So you start off with your product specification, which should push down into the block level. That then gives you what the designers will implement from, but also what the verification team will then use to analyze the design and work it out to test it. Ideal world, you treat the design as a black box, but particularly in the mixed signal space, you end up reaching a cross between helping the analog engineers understand how the digital work and vice versa. So it's not quite as clean as the pure DV realm. And what you end up happening is it tends to actually be almost with mixed signal chips is almost a conversation between verification challenging the specification and finding the holes, verification challenging design, say you're not necessarily correct, but equally design saying to the verification, no, the chip shouldn't really work that way. And so it's a more interactive process for mixed signal chips. But fundamentally, you still hit the same point that at the end of the process, you've got to be able to say you have confidence that what you give to the customer will be good enough. So that's that. And I think it's on to you, Pete.
I was just going to add on that.
Go for it.
No one writes War and Peace as a specification, and as an engineer, no one reads a manual. So you do all this documentation, and it's never often checked. And because I'm getting some shakes in the audience, but it's true. Who opened up the iPhone and then first downloaded the manual and started reading 10,000 pages on how to use your iPhone? No one. I mean, I installed a dishwasher last weekend. I just threw the manual straight into the bin and started fitting it. I'm an engineer. I should know how to fit it. Yeah, that's what I do with the Cadence software as well. Right, onto a very simple analog circuit. So this is going back to your second year university days. So some golden rules of an op amp. We've got infinite gain. We have no current flowing into the inputs, and there is no potential difference between the two inputs there. So rule 3 basically means that voltage there and that voltage there should be the same. If we then do the calculation of the current coming in there, we end up with this equation. So we get I in is V in divided by R in there. We can then do the same calculation on the output. So we've got 0 there. That's V out. So you get the equation there. Then putting rule 2 together, we know that I in and IF are the same. So we can join the whole lot together to get that single equation. Oops. Basically, you've got an integrator, inverting integrator. So if we take that to the next level, and I basically add some voltage sources on here, some switches and a resistor, I could turn those switches on and off to add different voltages onto that node. So if we go through some maths, we can assume S1 is either a 0 and 1, then it's either adding the current coming from that branch or the current coming from that branch, and then that will go out onto this one here. So we can do a very simple equation and say V out is basically the inverted version of all the sums of the voltages divided by their resistance based whether they're on or off. So in a simple case there, you've got, you know, S to the N number of switches, so you've got N number of combinations. Ooh, so what I'll do is Graham will tell me how you're going to verify it next.
So what we're going to go through now is just sort of stepping stones as to why analog mixed signal verification needs to move on. So this is traditionally how you'd set up an analog test bench. You've got, so it's got a pointer on it as well. Yeah. So you've got your power supplies up here, you've got a cap on the output, your grounds, and what you've got here is what you call PWL statements, which are time voltage pairs. And from these time voltage pairs, you can then generate we're doing 3 codes here, and you get 3 voltage steps out. So you've got a very simple verification of this block, which is something, well, that's fine. But if you consider that to what Mike and others have been talking about, if you got a chip with sort of millions of states, imagine trying to verify it like that. You imagine trying to generate all these individual states like this. It's going to be impossible. But going back to what Mike was on about with unit testing, analog engineers tend to focus on the performance of the block. Does it meet your noise figures, your power consumption, and area and other things? That's their focus. And they will use their test benches to target that, but they will not be targeting the scale that we need when you've got millions of states. And these simulations are quite slow. So that doesn't really help. So anything else to add on that one? Was that that's good? So then if you move on to digital design, as we've been discussing, so you've got everything's abstracted, you've got everything in RTL, and your stimulus is now onto sort of multi-bit reasonable frequency. You've got different ways of controlling the gain. You've got resets and other things on there. But fundamentally, and this somebody should mention the other slide, usually for a digital designer or for an analog designer, the focus is on waveforms to review. It's not on self-checking. It's not on big picture. Will this work as a system? So that's the sort of limitation when you get to this point.
So DUT, the digital hardware, is written in RTL, and that is something that can be translated to logic gates. But System Verilog that we write the RTL in is not only there for doing hardware design, but actually can be used to do the stimulus. And it's very much a software language based on C. So it's got objects and classes, etc. So what this has allowed people to do is, instead of testing the design with sort of waveforms like the analog people do and hardware like stimulus, you can apply a software layer to it. So now the software is going to drive the hardware component. So you've got on the slide there some of the input stimulus, but that will be driven by a software layer. The functionality is being looked at rather than the performance, because the performance is fixed in hardware. What you're looking at is, I drive this input, I get an output. I use a predictor model that is meant to emulate the hardware design, and I compare the two outputs and I get a pass and fail. And this means that what we can actually do is, using software techniques, do constrained random input stimulus and then self-checking on the output. And we should be able to get 100% coverage. So this is sort of the digital methodology going forward. And that's it.
Okay. Thank you so much, Peter. Thank you for covering grimy slides.
Yeah, I needed the recording because I needed to remember what he had said in the previous slide. So I made some notes.
Okay.
Yeah, and I'll be in touch with the verification futures as Mike sort of got me